Okay, so I'm going to do the first part of the talk. And so we are going to talk about CRDTs. I'm very happy to be here because this is my first in-person meeting after the start of the pandemic. So it's great to see people around the real audience. So we are going to have two parts of the talk. The first part will focus on some high-level view on CRDTs. We'll try to explain a little bit of the jargon and get you an idea of how the things work. And then Nuno will come up and explain more complex things like multi-object operations and keeping invariants in the system. So first I will try to motivate why we need these kind of things nowadays. So this is a map from the 19th century from Francis Galton, that was a pioneer of statistician. He was involved in the creation of the standard deviation. And he made this isochronic map. So this shows the travel time that you could get from London until any part of the world. And it was a travel that used just buying a standard ticket. So you can see that some regions are harder to reach than other regions. You have the scale over there. And some places you took a full month to reach them. So this was kind of the speed of the communication a little more than 100 years ago. Then I did a small measurement when I was making those slides. So this is the round trip time that you can experience. So you can see that if you are communicating, for instance, within Europe, you can communicate like less than 50 milliseconds. But when you try to go across the ocean, you quickly get into the 200 milliseconds range. And in a way, this is limited also by the speed of light. So we cannot do much better than this within the confine of our planet, because the planet has a given size. And this will limit the way that we can handle data across the planet. And things will only get more complex as we get outside the planet. So if we are trying to handle data that is within the solar system, we are looking at round-trip times that will be almost close to 1 hour. So it will be hard to use certain kind of protocols in this setting. So let's look at what protocols we might be looking at. So suppose that we are handling data and we want to keep data synchronized, have a common view of data. We can look at two latency scales. So small lambda is when you have data close to you, when you are close to the server, the client is close to the server that is being contacted. And we have the big lambda when you need to go and do intercontinental communication. So if you don't have replication across the world, you can operate with just a fast communication, the small lambda. But once you try to have geo-replication and serve clients all over the world, you are faced with some choices. So you might opt to go for strong consistency, not allow any divergence of the data. And at that point, you need to use some variation of paxos. You need some consensus algorithms. But that also means that you need to pay a price in terms of latency and responsiveness. You probably need to pay a little more than 200 milliseconds to do this kind of coordination. Then you have some middle ground. I'll not get into it, the primary backup. But if you really want responsiveness, then you need to get into a multi-master system where you allow clients to communicate their updates locally to the local server, but then you get divergence in the system, and then you have to deal with divergence. So this talk will be about how to deal with divergence. So you cannot solve all the problems with weak consistency. So we are getting into the weak consistency sphere, but you can solve a lot of problems or a lot of stages of problems with weak consistency guarantees. So for instance, if you are talking about making an auction, you might be able to collect the bids using a weak consistency approach, a high available approach, but then you might need to have some consensus stage to close the auction and see who the winner is. You cannot get everything from a real system. So I guess many of you probably heard about the CAP theorem. Can you raise your hand if you heard about the CAP theorem? Okay, so you know that you cannot get all the good things from the system at the same time, okay? if you cannot rule out partitions, which normally is the case, then if you want to keep being available, having high availability, you need to release a little bit of consistency in the system. If you want consistency, then you might have to wait for the result. So CRDTs will help you work in the high availability sphere of the equation. But first, let's see how we can get there. So first step is to look at a sequential execution. So if you are running a consensus protocol, you are kind of simulating with state machine replication that you have a single replica that you are acting on. And if you look at a single replica, there will be some math, but I will try to go easy on the math. But what you need to see from here is that you have a total ordered sequence of operations. You have your log of operations in a total order. So we have a single sequence. And if you have a single sequence, it's easy to know the outcome of the state of your object. You just apply all the operations and you see what is the resulting state. So this is the easy case where you have a single sequence. But if we keep doing this, we need to pay a latency price. Now, if we get into multi-master setting, then we start having divergence in the system. And this means that you no longer have a sequential log. Now you have a partial ordered log of operations. So this means that you might have an operation node that was done at a site. It was communicated to a site on the top, another on the bottom, and you do some operations on the top, other operations on the bottom. Then you communicate back to the middle, and they synchronize. So in this case, you have some operations are related in an order, like P was after O, but you have operations that are concurrent. So when you cannot find a relation by the arrows, that means that those operations are concurrent, and you might have conflicts between these operations. So we have two cases here. P is concurrent with S. So CRDTs will help you reason on this kind of executions where you have a partial ordered log of operations. And it provides data types to do some known things from sequential behavior, like you can have a counter, a set, or a register. The registers will get a little bit strange, but we'll see that. There are two ways to approach CRDTs. So I'm not going to get too much into detail in the two ways, but one is based on operations, and the other is based on the operation on state, on controlling how the state can evolve. You can get a message that the two ways are equivalent. You can emulate one by the other and vice versa. So first, let's look at the operation-based way. So the idea is to get effects of operations that are commutative and that you can apply in any given order, or that at least if you deliver all the operations in causal order, when you get concurrent operations, we can apply in any order and you get the same outcome. But for some data types, you already have that even when you are doing sequential operations. So here there are two examples. One is a counter. So if you look at a counter that starts at 0, either you first decrement and then increment, you end up with 0 again. So if you switch the order, you get the same outcome. So a counter with increments and decrements, you can shuffle the order of the operations that you get the same outcome, as long as you apply the same number and type of operations. The same thing goes for sets. If you have a set, a very simple set, where you can only add data to the set, if you are adding different elements, it does not matter the order in which you add the elements, you get the same end result on the set. Now, when we get into describing the state-based CRDTs, I'm not going to get into the details of this slide, so this is all the mathematics behind it, but I will try to get you an intuition into this. So the idea is that you start with a state, you have an object in an initial state, and you have, say, methods that will change the state of the object. And the idea is that you must make the state changes in a way that you are always incorporating information into the object. So when you add things to the object, to a set, you need to incorporate information. You go upper in the evolution of information incorporation. In mathematics, you go upper in the lattice order. But also when you delete things, you should not go to the previous state. You must also remember that you deleted something so that you are able all the time to pick different instances, different copies of the object, and reconcile them and get the correct reconciliation. So this is called a join operation, and technically this is a join semilattice. I will try to show you the intuition with a small example. So if you look at a set, we have a set here that starts empty. So mathematicians have this very nice symbol called bottom to represent that. So that is an empty set. And if you have an empty set, you can involve in different ways. You can add the element B in a replica. Another one, you can add the element A. And if at some point you decide to combine this information, you will get AB. So the combination of information here is a set union operation. So this is a concrete example of a joint semilattice where you are adding elements and you are combining, you are joining by doing set union. So the idea is to do this for more complex data types and get useful data types that developers can use, although they might be tricky to make work. So when we are looking at this, there is another message that I want to convey, is that you can do any CRDT just by keeping the full log, the full partial ordered log of all the operations that occurred in the system. The problem with this is that this takes up a lot of space and might not be very computational efficient to query, because there's lots of dispersed state. But with this, you can make everything. So if you look at this sequence of operation and you start at 0, you know that the end value is 3 because you have 4 increments and 1 decrement. So actually, you can look at the operations there, and the counter value is just counting how many increments you did and subtracting the decrements that you did. Again, you can make this work for any set of operations. But the idea of CRDTs is to make it more efficient than keeping the whole graph. So how do we get there? To get there, we need to have some ground rules. So one of the ground rules is that you need to have this principle of permutation equivalence. So if the intersequential data type, so the trick is to build a concurrent data type from a sequential data type. If in the sequential data type the operations already commute, we have 2 different sequences of the same operations over there, then when you put those operations in a concurrent execution, you need to have the same result. Okay? So it will be very strange to have a concurrent execution with the same operations that already commute that yields a different result. So this is one of the ground rules. Here the result is always 42 for some reason. And now the idea is, how am I going to implement this? As I said, I don't want to store the whole graph of operations and be looking at that graph, at that whole log all the time. So here we have some concrete operations in specific replicas A, B, and C. So we have 2 increments on replica B, a 10 and a 2 in the end, and an increment over there and a decrement in the bottom. So the way to implement this is to store the state in a given way in the replica. So for each replica, we are going to store a pair, and the pair is going to have the number of increments done in the replica and the number of decrements done in that same replica. And we will going to do this for all the replicas. You will see that we are going to implement a mergeable data type with this. So in replica B, we already have over there in the beginning the 10 increment over there stated. So when you replicate it to replica A and B, you get the B10 0 on the 2 sides. But now you can also do some operations on replica A. So more increments on replica A. And as you see in replica C, you did a decrement. So you represent it on the right-hand side of the pair. And you can keep operating on each replica. And at some point, you can transfer the information again to replica B. And at this point, replica B must have a deterministic way of combining the information in a way that will preserve the end result. So what it does is that it does what we call a pointwise maximum across all the entries. So it will look at the information from replica B from both sides, and it will do the maximum between the 2. The result will be B10 0. But then, if you recall, we did an extra increment on when we collect the information, so it becomes B12. So we combine the information by an operation that will take the pointwise maximums. What is interesting about this operation is that once you do this, you can retransmit all the previous states and join them again into the end state that you don't change it. So if you are using a communication protocol and you are not sure if you supply the information to the other side. You can retransmit again that you know by merging, you don't get more effects than you already collected. So this is an important property because communication is brittle and sometimes you need to retransmit information. So technically, you can do it this way. I'm not going to get into detail. It's a short spec and I don't want to bother you with that. But what you basically see there is that when you are applying increments, you are incrementing the right-hand side, the left-hand side of the pair. When you are decrementing, you are actually incrementing the right-hand side of the pair. When you look at the state, you sum the increments and you subtract the decrements. And the very important merge function, you do the pointwise maximum in a compact way. I don't have time to go into the details. Now let's look at another data type. So I looked at the counters. Now let's look at a register. So what is a register? So you can look at it as a sequence of write operations. And if you have all the write operations in a total order, it's very easy. So the value of the register is just the last write operation that you have over there. In this case, it's the X. So another important thing is that even if you have multiple replicas, you might end up with executions that are sequential. So this execution in the bottom, we did a write of X on replica A, then that information went to B, then we did 2 writes, but there is no concurrency going on. Although we are doing things in different locations, it's like if a location acquired the right token, did the operations, and released the right token, and allowed the other location to proceed. So in the end, we have a sequential execution that was done across different sites. Of course, in this case, the outcome must be the same that you will have if you did all the operations in a single site. So this is another rule. So how can we handle a register that is high available and that is operated on different sites? So one classic technique is to use what technically is the Thomas Wright rule, but it's more popularized as last writer wins. So what you do there on this approach is that every time you write something, you assign a timestamp to the write. And then you are only going to retain on the merge the value that is assigned the highest timestamp. But the problem is that for this thing to work, you need perfect clock synchronization. Otherwise, you get problems and you might get loss of availability or you might lose writes if the clocks are out of sync. So I have an example over here. Site A has a clock that is behind by 1 hour, so it does a write. Then it passes that information to site B. Since site B is ahead in time, there are no issues. It can write again. These writes will replace whatever it gets again from site A. Now the problem comes when you convey the information again back to site A. Site A might be unable to write. And even if it writes, when it sends information to site B might not be able to determine that this write is fresher. So it's very tricky to use clocks. There are better techniques. Clocks can still be used for disambiguating between concurrent writes, but as the primary mechanism, they are very tricky. So let's look at what is a register conceptually. So a register will show a given value V if V was written and there is no other write that overwrites the V. You have no other write in the future of V with a different value. So basically, this is what a register is. And when doing a concurrent implementation, a correct concurrent implementation of a register, you want to preserve these semantics of the sequential register. So let's look at the concurrent execution over here. And let's look at the concurrent semantics. So now the difference here is that we are comparing in the partial order. So that funny less than sign is just comparing in the partial order. So what is a register, a concurrent register? Is a register, actually in this case it's a multi-value register. It must show all the values that were written and not overwritten in the future, okay? So in this case, we have two concurrent writes, write of I and write of K, that were collected again on site A. And in this case, you have two values because these values were not overwritten yet. Later on, we overwrite with a merge and you get again a single value. So this is how you get a multi-value register. You collect the values that were written in different sites concurrently. And this is actually what happens inside the Amazon for the Dynamo shipping system. So when you are handling the shopping cart, if you interact with different servers for some reasons, because you are using your mobile machine to add a product and you use your laptop, you might end up with, the subsystem might end up with 2 copies. It will try to combine them and get again a single copy. So how can you implement this thing correctly? You can use a technique called version vector to tag each write. So you assign these tags in each site, and you can then compare and see that 2.0 is not comparable with 1.2. And this means that you get having 2 concurrent values, you can present them to the users, and you can merge them later. So this is what a multi-value register is. Again, this is a state-based CRDT. Now, let's look at sets, which will be our last example in this part of the talk. So what is a set? A set is something where you can add information to, and you expect some things to happen on the set. For instance, if you add elements A and B, you are expecting to observe that they are present on the set. But if you add a C and you remove it, you also expect that C is no longer there. So what is the specification for a set? A set has all the elements that were added, and for whose elements there is not a remove greater in the order to the add operation. So if you have an add operation that has a remove after it, the element is not present there, okay? So you cannot find a remove that is after the add, and this means that you keep that kind of element. So this fully specifies a set. Now, we will have some problems with some operations that will be conflicting. So let's look at this example. We added X, and then we changed our minds in the 2 sites, we removed X, but on site B, we added X again. So now we have a problem. When we combine this information, the last operations that we have seen is a remove of X from site A and the add of X from site B. So there is a conflict over here. Whatever decision we make in order to present X or not, we know that if we add X again, then X must be in the set. But we need to choose something for the outcome. And this is when the choice comes, and the choice normally is we give priority to the add operation, and this way we get what we call a add win set, or we give priority to the remove operation, and then we get a remove win set. So I'll just describe those. So what is an add win set? So an add win set will show all the elements that were added and for which there is no remove after adding the element. So if you apply this reasoning to this example, you see that X must be present on the set because there is a concurrent remove, but there is not a concurrent after the add. So is this familiar? Actually, this is very similar to the spec that I gave for the total order, for the sequential set. So another interesting property you get here is that if you end up having a sequential execution, you get the same outcome with this kind of specification. So you can also do this for the remove wins semantic. Before that, how can you implement this thing? And I will finish with that before transition to Nuno. So the way to implement this is that each time you add an element, you must create a unique tag that goes with the element. And each time you try to remove something, you must collect all the unique tags that you had with the element, and you put it on the tombstone set. And you are only going to present to the user the elements that are added and whose tags have not been collected in the tombstone set. So this specification works for that, and the merge is very straightforward. So I'm going to skip quickly the remove win set and stop with this take-home message. So you need to accept concurrent executions if you want to be fast. And if you have geo distribution, you have limits on how fast you can go with strong consistencies. So you might have to consider using weak consistency. And once you are trying to design these data types or trying to use them because they were designed by specialists, you might expect them to behave correctly under sequential execution. So it's quite important to preserve the sequential semantics. And the CRDTs have sound guidelines to provide this, and each CRDT that is done and is correct will already provide you with the correct merge procedure that you can use. So thank you. I'll switch to Nuno.
Okay. Thank you. So in this second part, what I'll be trying to show you is how we can build on CRDTs to do some more complex guarantees, to give more complex guarantees to the applications. Before going there, let's recap a little bit. So CRDTs have been used in lots of systems for guaranteeing that all replicas will converge to the same state, okay? So, and there are some systems that are basically built around a single object. It's a single object. For example, YJS, AutoMerge are systems that are mostly built around a single object. The object is complex in these systems, okay? They have JSON object that can be a very, very big object. Okay, and then we have another systems that we can basically define as generic databases. Okay, for example, Redis, Akka, React, or AntidoteDB, that is something that we have done. Okay, so in these systems where we have multiple objects, okay, what happens is that we will have multiple CRDTs. And these systems, what they typically do is that they handle each CRDT independently. Okay, so each CRDT has its own rules for converging, okay, but it's independent from other CRDTs, okay? And of course, this is good in a way because it gives and guarantees that all replicas will converge to the same state. But it has a problem. If we look at applications, okay, applications typically need more guarantees than just convergence. And if you see, well, for example, SQL databases have all those kind of integrity constraints like referential integrity, check constraints. So what I will be trying to convince you in this part of the talk is whether we can build on CRDTs to provide these additional guarantees. Okay, so let's see what is the problem with referential integrity and the problem when you use a weakly consistency system. So suppose we have two replicas, okay, and we have two sets, the kind of sets that Carlos has introduced. One set to maintain the information about the workshops that exist, and another set to maintain the registrations that exist. Okay, so I'm using sets because that's the ones that Carlos has introduced. Okay, so we have two workshops, CRDTs and NLP, and we have a single registration. N is registered for the NLP workshop. Okay, so as there is no registration for the CRDT workshop, we just want to remove the CRDT workshop. Okay, so no one is interested in that, so let's remove it. So the problem now comes if in another replica, we have someone that is interested in the CRDT workshop, and John wants to register in that workshop. Okay? In the second replica, in the registration set, I will have N registered to the NLP workshop and John registered to the CRDT workshop. Okay? So in a database that merges per object, okay, we end into a problem. So what is the problem? If you look at each object, we don't even have concurrent operations, okay? We have a single operation in each of the objects, okay? And we end up in a situation where we have only the NLP workshop, okay? And we have John registered to a CRDT workshop that doesn't exist anymore, okay? And this is a problem. And this is what is called in SQL databases a violation of referential integrity. Okay, and this violation occurs because we had an add and a remove, a concurrent add and remove, but instead of being done in the same object, they are done in different objects. Okay, so the first thing that we need to think about this is, so what do you want? Okay, so if we have this problem, okay, we want to solve this problem, okay? And we have basically two ways of doing this. So if we have had a problem with the N and a remove, as Carlos has introduced it, we can have an add wins policy, or you can have a remove wins policy. What would that mean in this case? So in this case, okay, if I have an add wins policy, that means that I want to keep John's registration, okay, but to keep John's registration and keep referential integrity, then I have to kind of revive the CRDT workshop, okay? This would be kind of the add wins policy for solving this problem. I can also have the remove wins, okay? In that case, okay, I want the CRDT workshop to be removed, okay? If the CRDT workshop is to be removed, I cannot have anyone enrolled in it, so I must kind of delete or forget about the registration of John. Okay, so, but the question is, can CRDTs help for this? Okay, and how can CRDTs help? Because CRDTs are designed to solve concurrent updates on the same objects. Okay, so if they are designed to solve problems on the same objects, maybe the answer is, okay, so let's force these operations to lead to concurrent updates on the same object. So how can we do this? So let's see the example. So we have the workshops. We will use an add wins set. And we have the registrations workshop. We have also an add wins set. Okay, if we remove the workshop, we do remove no fancy thing here. Okay, and the fancy thing comes here. So if we want to make updates concurrent on the same object, okay, I will need to kind of expand this registration operation, okay? Instead of adding only John on the registration on the CRDT workshop, I will transform this into two operations. One operation that will add the CRDT workshop again, and another operation that is the original operation that adds the registration of John in the CRDT workshop. Okay, and now this is fine. Okay, so referential integrity is solved here. And now when I merge, okay, now I have concurrent operations on the workshops. Okay, so in the upper replica, okay, I've removed the CRDT workshop, and in the down replica, in replica B, I've removed the CRDT. I've added the CRDT workshop. When I merge it, okay, as this is an add wins set, I end up with the CRDTs in the set. Okay, so and this is the idea to solve the referential integrity problem. We can also do it in the remove wins solution. Okay, so basically, the add operation in this case for remove wins, we just keep the add registration, and now for removing the CRDT, we need to do something a little fancier, okay? Because we want to do a remove operation on the set, but we want to remove any person that might enroll. So we need to have an operation that adds kind of a remove anything on the CRDT workshop. And with this, okay, we can merge and have John not being in the registration set. Okay, why? Because I have a concurrent add and a concurrent remove on the registrations for the same values. Okay, and as remove will win, John will not be in the set. Okay, so this kind of solves the problem of referential integrity. Of course, you are thinking that okay, so that's fine, but in a database, objects are not simple values. So adding again a full object is complex and could also lead to problems of concurrent updates. Okay, so what can we do? Okay, so basically we can kind of represent an object as a map or a JSON object or something like that that maps a column into a CRDT. So I've represented now in the replicas, I have the name of the workshop and I have the number of registrations available. Okay, and we'll need another column that will be a multi-value register that has information about if the column is visible or not. Okay, and when I insert the element, I put it to an I. Okay, saying that it was inserted. Okay, so now how do I remove the workshop? I remove the workshop by setting the visibility to D. Okay, D means that object or that row, how you want to call it, will be deleted. Okay, so how do I add? Okay, I add the John to the registrations objects, and now I need to go to the CRDT workshop and change the visibility from I to T. Say, doing a touch in the CRDT workshop. So when I merge, okay, the visibility is a multi-value register, okay? So for the CRDTs, I will get the D and the T, okay? So because I get the two values, the two concurrent values that were set. And then I will say that an object is visible if one of the values is either an insert or a touch, okay? So, and this solves me the referential integrity problem with a more complex situation where I have objects instead of having single values, okay? So, we can do it also for remove wins. I don't have time to talk about this here. Okay, there is a paper that you can try to find that explains how to do it. Okay, so let's look at the second example that I want to tell you. The second example is about counters. Okay, and about counters that have bounds. For example, the number of available places in a workshop. Okay, so I have the number of registrations that are still available, okay? When I register someone, I do the touches and I decrement the number of registrations. It was 29 for NLP, now it's 28. If I do another registration, okay, in the other replica is also 28. When I merge the counters, the decrements are merged and I end up with 27. Okay, this is fine. Okay, the problem comes. When does the problem come? The problem comes when we are really close to the bound. Okay, and when you are close to the bound, we end up into a problem. So suppose for the NLP workshop, I have a single place available. Okay, if I register Sarah in the NLP workshop in replica A, I would say that in replica A, I have 0 places available, okay? The problem comes if I have another replica that also thinks that there is 1 place available. And there is John that wants to register, okay? And in this second replica, I will decrement the number of registrations to 0, okay? And locally at replica 0, it seems that everything is fine, okay? Because I have 0 places available, okay? The problem comes when I merge the two concurrent updates. When I merge the two concurrent updates, I merge the decrements, I end up with the number of available registration to be -1, okay? I know that air companies don't have problems with that. They sell more tickets than that they have, but let's assume that we don't want to sell more tickets than we have. We come up with a problem. So how can this problem be solved? So a possible idea is to kind of assign the share of available places to each replica. The other alternative would be to have a replica that has the number of available seats, okay? And when I want to contact the replica, okay, I will go to the replica and see if how many seats are available, okay? But that would require that every operation will have to coordinate with that server, okay? And we want to do it in a distributed way, okay? So the idea that is implemented in something that is called a bounded counter is that, for example, we want to assign rights to execute operations, okay? So for example, if I have 2 replicas and they have 30 places available for the CRDT workshop, I will split the 30 between the 2 replicas and I get 15 each one, okay? And for the NLP, I have 15 and 14, okay? And if I execute an operation to register, if I have enough available places, I have 14, I have 15, I decrement one, I get 14 available for the NLP workshop. And in the replica B, if I register John for the NLP workshop, I go from 14 to 13. When I merge, everything is fine. I'm under the limit. So let's see the problematic case. Okay, so if I have only one place available, okay, I will have to split this place available by the two replicas. One replica gets one place available, and the second replica gets 0 places available. Okay, so in replica A, if I register Sarah in the NLP workshop, I get 0 places available. Okay, and in replica B, if I try to register John, okay, I would say that I cannot accept the registration because I only have 0 places available assigned to my replica. Okay, so in this case, the operation will fail, or alternatively, I could get writes from other replica. Okay, so this kind of solves the problem of having counters that have bounds. Okay, so kind of a take-home message from this second part. Okay, CRDTs guarantee eventual convergence. Okay, system-wide guarantees require more than simple CRDTs. Okay, so how can we address this? Okay, so as I show you, we can use and you can build on CRDTs to provide system-wide guarantees by wisely extending the operations, and we can design rich CRDTs where most of the operations can be executed without coordination. And only a few ones that really need coordination will have to coordinate. Okay? There are systems that are trying to do this. Okay? So Antidote SQL is a system that we have built. Vaccine.io is a system that, a database that is being built and that tries to adopt these ideas. Okay? So thank you. And I can take questions now.
Okay, so in the interest of time, because there was a delay also on starting, we can take maybe just one question and then we'll let the next presentation come in so that we can get ahead on the next section. But we will be available in the lobby afterwards if you want to ask us stuff about CRDTs, and then this way we don't delay anyone. So if there is a quick questions, we can take it, otherwise we'll just do it in the lobby, okay?
I get the only question. I hope you all have the same one. It seems like CRDT, the developer or the designer needs to understand the impacts between the data sets in the system. So in your case, workshops and registrations. Is there a modeling exercise, or is there a way to document those effects before you start building so that a developer who's going to actually implement this already knows what the business rules are around when, like for instance, when a workshop is removed, I also need to clean out the registrations that have been created on the other replicas?
Well, I think the programmer needs to know those rules. And if we go back to SQL databases encode those rules with referential integrity and things like that. Okay, so what I'm trying to convince people here is that maybe you can use the rules that people were used to use in SQL databases, like referential integrity, check constraints, and things like that, and move them to this kind of a weakly consistent world, but do those operations in a way that the operations can be done in an asynchronous way without coordination. Because if you do it in a SQL databases, you need to coordinate to execute the operations. Here, you kind of have to define that you have kind of referential integrity. For example, what we have in Antidote SQL is that we say that there is a referential integrity, and then we define what is the policy that we want for that referential integrity, if it's add wins or remove wins, okay? And the programmer needs to know that beforehand when it specifies the schema of the data, okay?
Okay, thank you.